I'm going to basically throw one blob of code over here, and then sort of we'll look into a little bit more detail on what exactly are these functions that are being used over here, because you don't need to understand every step of this, but there's a reason why some of these functions are used in a certain way, right? A very standard part of any driver code is what's called a probe function, right? And this usually gets registered as part of the driver. What that means is that when the kernel tries to load a driver, the driver should try to non-destructively probe the system. What does non-destructively mean? It basically means that if the driver straight away assumes that this particular peripheral is present at the address that the kernel gave, and then straight away starts writing data to it and so on, there is a potential that it is actually writing to the wrong device, right? And ideally we do not want that to happen, or if we have got the address wrong, I might end up completely writing to a different location altogether, right? So there are certain things where I need to be able to probe and find out whether such a device exists. At least I need to sort of probe this driver into memory in such a way that it is able to at least allocate its memory resources and get information about the connected peripheral in as clean a manner as possible, right? In some cases, what you might find is that you can load drivers into memory even if the device does not actually exist. That's fine, right? I mean, there's nothing actually fundamentally in the hardware which requires this. All that you need to make sure of is that the kernel at least is able to sort of allocate the memory and give you information from the resource map that it has got, saying that it believes that there is a device present over here, okay? So the way that it works is, right, this probe function essentially gets a pointer to a platform device, and it's trying to sort of allocate certain resources, right? So we can see that it does some kind of allocation of a particular structure over here, right? And essentially look at these are like standard patterns of code that you will find over here. You try to write one particular allocation function, and if that did not succeed, you immediately have to return with an appropriate kind of error message. In fact, in the kernel, unlike in regular C code, there are some extra sort of attributes of C functions that are used, where it is possible to specify that certain functions must have their return values checked, right? What does that mean? It's possible, after all, in C to write code where I basically call a function which returns a value, but then I don't check that value, right? One way of looking at it is, you might have seen that we usually, when we are trying to open a file, we declare something like file star fp, and then we say fp is equal to fopen something. Now we could do that. I could just say fp is equal to fopen, right? And I don't necessarily check whether fp has actually got a non-null value. I don't check the return value, right? In this case, what it says is, if you don't check, there is a possibility that the entire system will crash. So the first thing is, you do have to have something where you assign it over here, and then you need to check whether that succeeded or not, right? Now the reason why all of these are sort of put in like this is because the kernel is the the part of the code that's running directly on your hardware. If something goes wrong in the kernel and it crashes, there is nothing you can do. You won't even get a debug message, because even to print a debugging message, you need to have a kernel running, right? So this is one place where you have to be extra careful in every type of code, every allocation, every sort of checking, printing and so on that you use, so that you are reasonably sure that your system is not going to crash as a result of something that you do, okay? Alright, so we basically have this allocation function, and then you will find that there are certain things such as this platform get resource, IO map resource, set drive data, sysfs create group and so on, right? And some of these we'll just look at in a little bit more detail, right? The important thing is, you will find that there are some fairly complicated looking functions out here which are not part of normal C code, right? But when you write a driver, you are expected to use these functions. These functions essentially constitute the API, the programming interface through which you are allowed to talk to the kernel, right? And it's important that you use these because they are written in such a way that they minimize the chance of missing something going wrong, okay? So let's look a little bit more detail. For example, we have one of these functions is the so-called platform get resource, right? And what this does is that it actually gets this address and size. So for example, that 0x7, that number, right, that address location, and the size, the 0x1000, it pulls that out of the device tree or ACPI in the case of a x86 based system, right, and constructs a struct resource out of it. Okay, so we can see over here, for example, that this platform get resource is going to return something called res, right, which is basically a struct resource. Okay, and why is this important? Because it allows us to do exactly what we have been talking about so far, which is that I can pull information out of the device tree and put it into a format that can then be used by other parts of the kernel, right. So just to recap what we have been repeatedly saying about the device tree, this means that the driver stays data driven. I don't have to hard code any of the addresses, I can pull them out of the device tree. This function is the API function, right. Once again, like I said, API is a fancy term for a set of function calls, right. By making sure that you use this function, you are sure that you are able to get it out in a format which is standardized across the kernel and should give you the results that you expect. We have also talked about the IO remap function, right, which can basically be used in order to take a physical address and convert it into a virtual address, which can then be used inside your in order to access the actual peripheral that you are trying to talk to, right. But in this case, what we are doing is we have a more complicated API. It's something called devm IO remap resource. So what this does is, rather than giving directly a physical address and a size and so on, I just pass in this res, which is what I got from the previous platform get device, and by doing so it does everything for you, right. It basically maps the void IO mem star. It effectively internally calls IO remap, right, but in the process it also validates the resource. And one other thing is, when you do something of this sort, it also registers it in such a way that when you no longer need the driver, it can actually clean things up for you automatically, right. So by using these functions rather than just trying to directly call IO remap, you are ensuring that the kernel knows enough about your module that it can actually safely unload it and process it as required when the time comes for it to, that it no longer needs that particular driver. Platform set drive data, get drive data, these are essentially, they manage to create a certain amount of state per individual device. It also avoids the use of global variables across the entire kernel. You have to be very careful when using such things, right. But managing memory is one of the most crucial parts of what the kernel does in the first place, right. And using these functions sort of allows you to manage certain internal state corresponding to the device, right, without at the same time having to use actual global variables across the entire kernel. Now the sysfs create group, right, is one function call which very nicely can actually go in there and create a bunch of different attributes or parameters. In the case of the smart timer, we already saw that things like the control register, the period, duty cycle, the status, all of those ended up as, effectively they look like files and somewhere under the /sys file system, right. Somewhere there is one directory which contains a file called ctrl, called duty, called period and status, all of which I can inspect. I can either write values into them or I can read values out of them and I'll get different behaviors, right. So the advantage is just this one function call over here, along with certain extra functions that you have to write internally, right, because after all, this sysfs, for example, when I say cat and I try to read the contents of, let's say, the control register, it's not clear to the kernel how exactly it should print it out, right. Should it actually just take the raw binary value and return it to you, or should it format it in some kind of a string that's actually human readable? The typical idea is that, when you try to read from a file like that, you want it to be human readable. But then how does that conversion happen, right? All of that gets done by having certain additional functions which are there inside your module, right? But this create group is the part that actually sets up the entire virtual file system for you. So why not just use regular functions? I mean, like I said, you could use the IO remap, for example, and directly say, okay, this physical address, map it into a kernel virtual address so that I can use it. The point is that the kernel is a very large and complicated piece of code, right? And interestingly enough, right, what you need to keep in mind when you're writing code for the kernel is there is no libc. Now this libc is something which we don't even think about when we write a C program, right? But in reality, what we tend to forget is the fact that even something as simple as, let's say, printf or even put c, get c, right, those kind of simple functions which can literally either read a character or write a character, are actually functions that are written in some library and that you can call. That library is libc. The kernel does not have access even to those, right? So when you get to a kernel which does not even have access to a simple function like putc or getc, it turns out that the kernel needs to write its own set of different functions, right? Including, for example, when I want to print a message from the kernel, I cannot use printf, right? What I can use on the other hand is something called kprint, right, which allows me to, it's specifically meant for printing messages from the kernel. It is written in such a way that it is guaranteed to sort of send messages to sort of what's called the console, right, which as we saw is usually mapped onto one of the UARTs, right, and allows us to get debug information even if the system itself is not able to come up the way that we expect, right. So the kernel drivers must use the kernel subsystems. They are any driver that you write, right, even if you say, okay, I'm going to load this in only after the entire kernel has actually booted up, it doesn't matter, you are still not allowed to link against libc as part of a driver, right. This sort of helps with many aspects, including what is called lifetime, which means that when I allocate a certain amount of memory, I need to know for how long that memory is valid, and after that I need to be able to release it and get that memory back. Safety basically means that I should not have a problem whereby I try writing into the memory location, but that's actually reserved by someone else. And similarly, you could have different kinds of policies in terms of what is allowed to communicate with what at a given point in time, right? So all of these things need to be enforced by the kernel, which means that as long as we use these APIs, it helps the kernel to sort of keep track of that, okay? Again, our purpose over here is not to write generic device drivers or to work on improving the Linux kernel in any way. The focus here is entirely on writing device drivers for fairly simple specific kinds of peripherals that we will be creating later. The point is, even for a simple peripheral, you need to ensure that you follow certain rules in terms of how you write a driver. So even though you don't need to sort of know all of these by heart, you need to sort of be aware of the kinds of restrictions that are present when you are writing device driver code. Now similarly, right, I mean the fact, for example, we saw this thing over here where we could see that this set drive data and get drive data, they avoid the use of global variables, and one of the reasons for that is by directly using any globals or hard coded addresses, it breaks portability, right? Not just portability, it gets even more complicated when you bring in the notion of concurrency. Concurrency is when two programs or two processes could be trying to access, let's say, a given device at the same point in time. Now you might wonder, why would such a thing happen? Well, it's more common than we think, right? It could be something as simple as, let's say, even a keyboard, right, where I could potentially have the output of a keyboard being sent to multiple different things depending on where my window is focused. Of course, in this case it's relatively easier, I'm just sending data from the keyboard and it has to go to the appropriate device. What if, for example, two things want to print messages to the console and they want to sort of send messages out on some kind of a communication stream, right? At that point, I have this notion of concurrency. I need to make sure that they are not sort of both writing at the same time. I need something to ensure that the data coming from each comes one after the other, right? So those are like much harder problems to solve, but the kernel needs to be aware of those and needs to have ways of solving it, right? And in general, what happens is by using these devm based, the prefixed function calls, right, it also helps to prevent leakage of memory. Leakage of memory is a scenario where, for example, I might load a driver, it allocates a certain amount of memory, something happens and it crashes, and or it needs to be removed, but I don't actually free up the memory that corresponded to that particular device, right? That's one example of what could potentially be a memory leak, right? So these kind of things, by using these standard API calls, we minimize the chances of such things happening. So, right, once again, going back into the sort of overall skeleton of what a driver would look like, right? We looked at what might be there in the probe, which essentially says, okay, I need to load this driver. I would also have something which essentially corresponds to removing the driver, because at some point I might say that I'm no longer interested in this particular module. How do I remove it from memory? Of course, my kernel cannot access that peripheral at that point, but it could be something as simple as I want to remove a pen drive that's been plugged into a device. At some point, I need to be able to tell the kernel that this thing is no longer connected, right? Now, of course, what we are talking about here is not like USB. These are platform devices, so it's unlikely that I'm actually going to unplug my smart timer or something like that. But there still needs to be a way by which I can disable it. I can sort of remove the driver and say, okay, I'm no longer communicating with this particular device. Right? For that, I need to remove, and one of the first things is that I would need to call this, just like I call the sysfs create group, I would need a sysfs remove group, which basically goes in and removes everything else. And it turns out that because I actually had this devm based allocation, right, all of them automatically get freed up and unmaps it when the system is being removed. Okay. And finally, the way that it works is that I actually put in this struct over here, right, the platform driver, again inside my module code, which gives me all this information. So probe is one of the parameters inside the struct. It tells me that I should use this function, which I defined, called st_probe, as my probe function. Similarly, this function st_remove as my remove function, right? So whatever name I give here has to match with the name that is used over here. That's all. It's not like I always have to call it st_remove. I could give it a different name, but as long as I have given this name over here and it maps to a function name over here, that's the function that will get called when I disconnect the device or I want to remove the driver. I also specify what name should be used for the driver, and I have already got that, the struct array, right, which is the match table corresponding to the compatible string. So I use that also in order to specify what are the things to match against. And finally, I have this one line of code which basically says, use this struct and register a module platform driver with the system. Okay. So when we actually call this mod probe or ins mod or something like that, what ends up happening is this is the part of the code that actually finally runs, right? And it looks at all of this information and says, okay, I have these different functions that I need to register with the kernel, so that as and when there is a device over here, it will call these functions, and then it will, when you try to remove it, it will make sure that the data has been freed up as required. Okay. So this is sort of just to look at the skeleton of what the code looks like. We'll actually look at the code itself in a little bit more detail, right, and then sort of see how we can load it, compile it, load it up and run it.